All right. Well, I want to echo Don's welcome to everyone. As BJ said, my name is Chad Bender. I am an astronomer at the University of Arizona, where I work on the habitable zone planet finder spectrograph and also on the NUID spectrograph. I also am one of the co-chairs of the scientific organizing committee, and so I'm very pleased with the program that we have pulled together and how many attendees are actually here today. So first, I can advance my slides. That would be good. There we go. First, I want to echo the thanks, particularly to the local organizing committee. Elise Ferlin, Ellen O'Leary, Wendy Burt, Megan Crane, and Don Cholino have really been instrumental in making this workshop work. We started planning for this workshop almost a year ago and had a plan in place and that was going to work really well. And then 3 months ago, we had to not completely change it, but dramatically overhaul it to deal with moving it online. And they have figured out all of the logistics of that. And without them, it would have certainly failed. But also, on behalf of my co-chair, Heather Segla, I would like to thank the rest of the scientific organizing committee, and also two people who have helped an extreme amount on the hands-on sessions, Nathan Hara and BJ Fulton. So with that, I think we should go ahead and get started. And we had a brief kind of overview of the structure of the workshop from Don, but I wanted to touch on some of the scientific topics that we're going to get into. And I think this is important because the question feedback mechanism for this virtual meeting is a little different than if you were sitting in the room in Pasadena. And so it helps to plan ahead and know what questions you might want to ask. Know what parts of the workshop are really the most interesting to you, although hopefully everything is interesting. So today we're going to get an overview of the fundamentals of radial velocities. We're going to have a panel discussion that can include a discussion of error budgets, and we're going to learn about some basic instrumentation. Tomorrow, we're going to dig into data analysis, statistics, significance. On Wednesday, we have a series of speakers lined up to talk about the horrors of stellar physics and atmospheric contamination that impact the spectra that we're trying to use to characterize planets. And on Thursday, we're gonna transition to other ways to characterize planets or more advanced characterization that we can get through other spectroscopic means. As Don said, we have hands-on sessions each day this week. We have the panel discussions Monday, Tuesday, Wednesday, and Thursday, which I strongly encourage you to take advantage of. It's a good opportunity to ask whatever you might want to that doesn't fit into the talk sessions. And then the lunch or time zone appropriate snack on Friday. I know we have people from all around the world, so lunch is probably not appropriate for everyone. All right, so why are RVs important? That's what I'm supposed to be talking about here. So let's set the stage with some history. Astronomers have known for a long time that stars vary in brightness over short time periods. Short time periods, I mean days, months, years, human lifetimes, not stellar lifetimes. That's not what we're talking about here. So they knew that stars varied. But in 1783, I think there was a significant advance in that John Goodricke reported in a letter to the Philosophical Transactions of the Royal Society of London that he had measured periodic dimming in the brightness of algol. The event lasted, quote, about 7 hours and occurred about every 2 days and 21 hours. He observed multiple events over several months and had a friend who was also confirmed his observations. We knew the star varied previously, but his is the first account of periodicity. And so I copied out his summary paragraph, and it's a little hard to read. So I typed out the important bit here, which is, I should imagine that it could hardly be accounted for otherwise, that either by the interposition of a large body revolving around Algol or some kind of motion of its own, whereby part of its body, covered with spots or such like matter, is periodically turned towards the Earth. So he predicted there a binary star, or a heavily spotted star that was causing periodic variations in the light. Let's go forward a couple of hundred years to 1952 with Otto Struve, who published in the Observatory what I think is really a seminal and fascinating paper. It is 2 pages long, actually slightly less, and it takes 5 minutes to read, and every word in it is important. So I've copied out a few important things here. One of the burning questions of astronomy deals with the frequency of planet-like bodies in the galaxy which belong to stars other than the sun. But how should we proceed to detect them? At the time, astrometric techniques were being used by Van de Kamp and others, but Struve recognized that these techniques required such precise measurements that they could only be applied to a very small number of stars. And in fact, we know now that the early reports of astrometric detections were in fact incorrect and dominated by measurement noise. And it's only recently in the last 20 years or so that we have bona fide astrometric measurements of planets. So he went on to say, there seems to be at present no way to discover objects of mass and size of Jupiter, nor is there much hope that we could discover objects 10 times as large in mass as Jupiter if they are at distances of 1 or more astronomical units from their stars. But, and this is why this paper is so compelling, he goes on to solve this problem or to propose a solution. There's no compelling reason why the hypothetical stellar planet should not in some instances be much closer to their parent stars than is the case in the solar system. We should test this. And if a planet exists at a distance of 1/50th of an AU, its period around a star of solar mass would then be about a day. So Struve predicted in this article the existence of hot Jupiters, some 40 years before we discovered the first one. And he goes on to say how you might measure this. If the mass of the planet were equal to that of Jupiter, it would cause the observed radial velocity of the parent star to oscillate with a range of 0.2 kilometers per second, a quantity that might be just detectable with the most powerful Coude spectrographs in existence. A planet 10 times that would be very easy to detect. And Andreas Kornbach is going to talk about instrumentation later today, if you don't know various flavors of spectrographs. And Deborah Fisher is going to talk about relative velocity scales to put 0.2 kilometers per second into context. So here is, I'm just going to go really quickly through a very basic primer to try and make sure we all start off the workshop at the same page. I'm sure this is a review for hundreds of you, but what we're measuring is the Doppler shift of the light from the host star. The planet causes the star to orbit around the center of mass of the system, okay, to wobble. And so what we see is the star moving its relative motion along the line of sight from Earth back and forth like this. If you can see my cursor, which I don't know if you can, but hopefully. And at different positions in the orbit, so we've got the star here, the planet here, the center of mass here. At different positions in the orbit, the star in this position is moving left to right. And so the velocity that we measure of the lines is the rest velocity of the spectral absorption lines. At this position, the star is moving away from the Earth. And so you have a red shift. So the lines are shifted to the red. Here, you're back to the rest position. And over here, the star is moving towards you and you're blue shifted. If we take lots of measurements like this and combine them together and then phase fold them at the orbital period, we can build up a velocity versus phase plot, which we can then use to measure some things about the orbital characteristics of the star and of the planet. So why are RVs important? this is really the crux of it. RVs allow us to measure the mass of the planet companion. This is a dynamical mass. It's a fundamental quantity, and it's derived mostly independent from stellar evolution models. You have to make some assumptions about the mass of the star. But apart from that, it's a dynamical mass. It's not a mass that you get from measuring the brightness of a star and estimating its distance and going to some stellar evolution model and looking up luminosities. So how you get there is straightforward, and I think Jason Wright tomorrow is going to go into this in more detail, but I just wanted to make sure that this was down on a slide somewhere for your reference. We start with Kepler's third law. We derive something called the binary mass function, F, which casts orbital parameters that we can measure, period, eccentricity, semi-amplitude, which is this measurement here, in terms of the masses of the star, the planet, and the inclination. This inclination term is important. It's hard to measure. It's impossible to measure with radial velocities. And so it's difficult to disentangle the mass of the planet from the inclination. This simplifies a little bit for planets. This is the general form for binary stars. It simplifies for planets a little bit because the mass of the planet is irrelevant relative to the mass of the star. All right. So let's move forward a little bit in the history lesson to 1989. And this is an important paper. There was a first generation of precision radial velocity spectrometers. I call it a first generation. It's really not if you include the ones that Otto Struve was using, but for EPRV sense, it's really the first generation that had been working through the 1980s to survey nearby stars. And this publication is the result of a survey to measure the radial velocity of stars to improve the RV reference frame for the IAU, the International Astronomy Union. This was a report of a orbiting companion, 84-day period by David Latham in Nature with a low velocity amplitude of 0.6 kilometers per second, which implies that the mass, if the system is edge-on, could be as low as 11 Jupiter masses. Dave went on to say the companion is probably a brown dwarf and may even be a giant planet. And I think until about 9 months ago, everyone on this panel and everyone teaching at this workshop would have said that this was likely the first exoplanet discovered. However, that is now in doubt because Gaia astrometry was used late last fall to measure the inclination of this system to be only 5 degrees. So it's nearly face on. So that inclination term came back to bite us here. In that scenario, this planet is 140 Jupiter masses, so a massive brown dwarf. So let's move forward to the first bona fide planet detection, setting aside the pulsar planets, which are kind of unicorns. But the first radial velocity detected planet in 1995, 51 Peg, which resulted in the Nobel Prize in Physics last year. And this was really a seminal detection. It was the first solid detection of something that was clearly planet mass. And it was a hot Jupiter, as predicted by Struve, that might exist. But it was something that is entirely different than anything in our solar system. So from that point on, we were finding planets at a steady rate, mostly through radial velocities. So here is 1995. There are a few other planets in here than just 51 Peg because of the pulsar planets. And this plot goes up to 2010, which I put as a significant break point, because at that point, something changed in the field. Really, what changed was mostly, again, predicted by Struve in 1952, which is the wide field precision photometry revolution. That's what I've called it. This started in the early 2000s. Struve said there would, of course, be eclipses for these short period large planets. Okay? The geometric argument is straightforward, and you expect there to be a large number of eclipses. These should be ascertainable by modern photoelectric methods, even available in the 1950s. Now, they didn't happen, but He thought that technologically they were possible. And the advantage of going after systems like this that he saw was that you can access fainter limiting magnitudes of stars. There's another huge advantage, which is that you can do photometry over giant wide fields, whereas spectroscopy is very expensive and requires targeting essentially one object at a time. So in 2006, we had the Corot mission. In 2009, the Kepler mission, and just a couple of years ago, the TESS mission, which have really revolutionized the field and found thousands and thousands of planets, leading to this. This plot is a few years old. It ends in 2017, but you can see we were ticking up steadily with RVs, and then the space photometer missions turned on, and it just shot and rocketed up. So in this paradigm, are RVs still relevant? It's a reasonable question to ask. Here is that set of planets plotted a little differently in terms of planet mass versus orbital separation from their star, which allows us to start looking at what different populations of planets do we have from an orbital construction sense, and also where are the different techniques that we've been using sensitive. So there are 4 primary techniques: radial velocity and transits, which we've already talked about; microlensing, which we're not going to talk about, but you should go back and look. I think there was a Sagan workshop on that; and direct imaging, which is applicable to a handful of very widely separated planets. It's really working on the other end of parameter space from RVs and transits. Transits, as you would expect, detect planets that are very, very close to their stars in short period orbits, because the geometric likelihood of a transit is larger the shorter the orbital period. Radial velocities work over a wide range in separations, all the way out to a few AU. And both work over a wide range of masses. There's 2 different populations of transits here. One of them is the space-based detections, and one is a ground-based, mostly detections. There's a little bit of mixing between them. But, so transits have found the most planets at this point, and they constrain the planet-star radius ratio. But if you want to dig deeper into what is the planet made up of, then you also need a mass. And measuring the mass usually requires detection with another technique, and RVs are usually the most tractable for terrestrial planets. With radius alone, you know the size of the planet and its distance from the star. With a mass, you've got the bulk density, and now you can start to constrain planet composition models. So here's a plot from Courtney Dressing from a few years ago, where she was taking what at the time was a very small number of planets with good mass and radius measurements, and trying to see where they fell on various models of interior planet construction. And she will be talking on Thursday, and I encourage you to ask her questions about this. So where are we in the RV spectrometer landscape? So we talked about the first generation of instruments. The second generation of instruments is the one that I think is the most famous, the 1990s through about 2010. These are the ones that discovered most of those early RV planets and have done most of the RV follow-up work. HARPS is probably the best known, and it has a maximum precision of something like 50, 70 meters per second. But in general, this generation of instruments can get you to a meter per second, and really not much more than that. In the early 2010s, we saw development of a third generation of instruments that are just now coming online that are targeting 30 centimeters per second or even better. This is NUID, Express, Espresso, KPF, and others. At the same time, we also had a generation that doesn't really fit into my chronology here, but of near-infrared spectrographs going after lower mass stars, because low mass terrestrial planets are more accessible around lower mass stars. The Doppler impact is larger and the orbital periods are shorter. So over here we have a plot showing parameter space of temperature of your star, orbital period, and this swath here from Jim Castings, who will be speaking on Thursday, is the habitable zone. And these lines sweeping down through here show approximately where in parameter space you can probe to with different sensitivities of instruments. So here's HARPS right here, and this region of the plot is accessible to HARPS. Caveat that HARPS is a visible light spectrograph, and so isn't all that sensitive to infrared photons where these M dwarfs are peaking. So the 30 centimeter per second instruments are up here, depending on how many nights per year, and there's a lot of survey calculations that go into this. But you can see that they are not quite getting up to where you need to be to detect Earth around the sun. And that's why we need another generation. So the question is, what do we mean by EPRV? EPRV, I think, is something that can detect the Earth around the sun, which is a 10 centimeter per second Doppler wobble. It's not just an instrumental precision, though. It's sufficient number of observations, sufficient time on the telescope to get hundreds of observations per year at that level of precision and be able to combine them all together. This is important because these are the top targets for the future direct imaging missions, and you should ask Sam Halvortson later in one of the panel discussions all about error budgets and how you actually determine that your instrument can give you 10 centimeters per second. So why are we doing this? There was a National Academies report that came out about 18 months ago, and it had a lot of questions about planets in there, but these are the ones that I think are relevant to EPRV. How do stars and planets form and evolve? More planet detections, particularly more low mass planet detections, help us complete the census of a diverse population of planets and measure the bulk composition. What environments are potentially habitable? If you want to do atmospheric spectroscopy and characterize your planet directly, it helps to know what the planet mass is so that you can put your atmospheric measurements into context. And then kind of the greater humanity question, is there life outside of the solar system? NASA is seriously considering launching a very large, very expensive direct imaging mission in the 2035, 2040 timeframe to go after biosignatures on planets. If you have a precursor survey, which EPRV can provide, then that mission becomes much more efficient. And Scott Gowdy is going to talk a little bit about this on Wednesday. So this is my final slide. How do we get there? Well, the goal, I think, is to build on the lessons of the second and third generation spectrometers, to build a fourth generation with precisions of 10 centimeters per second and intrinsic stability in the hardware at a centimeter per second. We want it to be able to discover Earth twins, explore terrestrial planets as a population, support space imaging missions. I see my Lisa's gone red, which means I'm way over time. So how do we get there? Well, Scott on Wednesday is going to tell you about a technology roadmap that we've been working on called the NASA NSF EPRV Working Group. Nathan Hara on Tuesday is going to talk about how we deal with these huge data sets that are going to be coming out of this, how we learn to combine signals, identify weak signals, deal with noise. On Wednesday, we have a really interesting set of talks about stellar activity and its impact on RVs by Heather Segla, Annalie Modier, and Jen Burt. And also on Wednesday, telluric impact on RVs by Colin Blake. But really, I think the most important thing that we need is we need people. And I really hope that many of you in the audience are some of those people. We need a generation of new students and postdocs who are interested and enthusiastic about working on this. And so I encourage you to get in touch with the people you're working with already, or if you're looking for to expand your careers, to get in touch with the panelists and really dig into this field. You know, when I joined it 15 years ago, I thought I had missed the boat, but clearly that's not the case, and you have not either. So, you know, get to work, and I'll stop there.
Thank you, Chad. Okay, so we have some questions I'll ask. Okay, so we have two that are kind of the same. Let's ask this one from Hitendra Singh. So there are usually multiple planets around any star. How do you see their effects on the star wobbling?
So I think Jason is going to get into this in more detail tomorrow, but effectively you can think of each signal as its own amplitude and period, and you add them, they co-add together. So you end up with a very complicated multi-frequency signal that if we had really, really high signal to noise and a lot of data points, if it was a physics experiment that you were measuring in your lab, it would be really easy to disentangle this small number of frequencies, 2, 3, 4 frequencies. But with the instrumental precisions that we can achieve and realities of photon signal to noises and things, this actually becomes very, very messy and hard to disentangle these. And so you need huge numbers of observations to do it. It's been done many, many times. Many of the planet systems that we know about now are multi-planet systems and have had their planets disentangled by RVs. So it's certainly tractable.
Okay, and then we have a related question from Jeffrey that just wants to go a little bit more into the detail. Feel free to suggest another talk that might be more appropriate. But so is there a Fourier / frequency analysis component to detecting these radial velocity planets?
So there is, and that's a technique that is commonly used, at least to get the initial period measurements out. And I think we're going to hear more about that both with Jason and also with Sharon Wang tomorrow. Tomorrow morning, we've set aside the entire day actually to talk about the significance of planet detections and the techniques that are used. And this is also something that you're going to do in the hands-on sessions. We're going to have you actually take real RV data and pull planet signals out using these common techniques that we'll use. So I'm going to pause on BJ.
Thanks. Will space missions for RV help in detecting more planets just like it did for transits?
So yes, I think that Peter Plavchin wrote a seminal report that came out a little over a year ago that was a concept study for a space-based RV mission. And I think that he showed that this could be very, very successful. The downside of it is that every time you go to space, things become orders of magnitude, not one, several orders of magnitude more expensive than on the ground. So a typical ground-based instrument right now, NUID, Espresso is a little more expensive, but NUID and Express are a few tens of millions of dollars, which is expensive. But if you go to space to do this in space, it will be $1 billion. And you still are left with the situation where you can only observe one star at a time. So you have an observing cadence problem, which I think someone is going to talk about later, maybe Gilbert, I'm not sure. But that problem is more tractable if you've got lots of observatories around the globe that can work in concert together. Space, it's hard to imagine that we could ever afford more than one platform. So there are some definite trade-offs to going to space. There are huge advantages, but there are some serious trade-offs.
Okay. Can we detect planet-planet interactions with current instruments?
We can. And in fact, I'm not going to go back in the slides, but I had a caveat on the slide where I said you need radial velocities to get a mass. And the caveat was, except for a small number of systems where we've got planet or planet-star interactions that we can see in very, very precise photometry from Kepler. Transit timing variations. So this is, you predict the transit, you know the period of a planet's orbit, and you predict when the next transit will be, and you go and you look for it in the time that the transit happens, either is a little before or a little after, so it's off from your prediction. And the reason it's off is not because your period was bad, but because there's another planet or multiple planets in the system that are also tugging it. So if you have those planets, and you know they're there, particularly if you have transits from each of them, you can do a full Newtonian solution, which has been done for a small number of systems, and you can derive masses independent of any other data set, so just from the transit photometry. But the number of systems that that's applicable to is very, very small, and it's not really sufficient to do the kind of population studies that we really need to do.
Okay. I think we have maybe one more. Do we have time for one more? Okay. So this is an interesting one. So what is the center of mass object in every system? I know you mentioned pulsar planets at one point.
What is the center of mass object in every system?
Yeah, is it always a star?
Oh, right. So it's usually a star. In the case of the pulsar planets, it was a star. So I don't think we have any planet systems where we have a black hole at the center, but I might be wrong. But it's generally a star. But the center of mass is, of course, not at the center of the star. The center of mass in our solar system is near the surface of the sun, actually, and that's offset because of Jupiter's tug. So it's usually a star. Yeah.